Hello. Today's lesson we're going to be discussing the properties of light. Light is all around us. It helps us see, helps carry energy, and it behaves in some surprising ways. But what is light? In this lesson we're going to explore its key properties such as wavelength, frequency, and energy. We say that wavelength uses the lowercase Greek letter lambda to describe the distance from consecutive crests or troughs. So if I were to draw a wave, this distance from here to here will be one wavelength. Okay, from trough to trough will be the same distance. Frequency, using the lowercase letter nu, it's the number of waves that pass a point each second. The speed of all electromagnetic radiation, or ER, travels at c, which is the speed of light, which is c equals 3 times 10 to the 8th meters per second. Okay, we have a relationship where c equals lambda times nu. So the speed of light is equal to the wavelength times the frequency. So this is speed of light wavelength in meters frequency can be measured in hertz, waves per second, or simply seconds to the negative first power. Let's discuss different forms of electromagnetic radiation. Okay, we'll start with radio waves, followed by microwaves, infrared or IR, visible, UV, ultraviolet, X-rays, and gamma. Okay, this visible light, let's take it and break it apart into Roy G. Biv. These were arranged with the largest wavelength at the top and the shortest wavelength at the bottom. The frequency will be the inverse of this. So the frequency would increase as I move downward. And energy will also increase as we move downward. At the end of the 19th century, physicists were very cocky. They thought that they had pretty much a theory or an explanation for everything that happened in the universe. And it was rumored that students were discouraged from pursuing careers in physics because everything had been discovered. Well, that couldn't be further from the truth. During this time, it was thought that matter and energy were two distinct things. Matter consists of particles, while energy was considered waves, massless. All that changed in the early 20th century with Max Planck. He was studying blackbody radiation. Blackbody radiation is where you're heating an object which does not produce light. He heated it to a temperature in which it started producing light. he knew that heated objects only radiate certain frequencies. That energy can only be gained or lost in only whole number multiples of a certain quantity. He came up with this formula where energy was equal to some integer times his constant times the frequency. So energy in joules, this is just an integer, like 1, 2, 3, etc. Okay, this is called Planck's constant. .626 times 10 to the negative 34 joule times seconds. And then frequency here is measured in hertz. He said that these small packets of energy were like quantas of energy. Einstein proposed that electromagnetic radiation can be viewed as particles or photons, which led to the dual nature of light. He said that light could behave as particles and as waves or rays. De Broglie soon found the relationship between mass and wavelength. Okay, so for a particle, his formula says that mass is equal to Planck's constant divided by the wavelength times the velocity. So this is mass in kilograms, wavelength, velocity, that'd be in meters per second, and Planck's constant. Okay, let's work a few problems. Fireworks uses strontium salts to produce red light with a wavelength of 650 nanometers. What is the frequency of this light? So, first of all, wavelength is equal to 650 nanometers. And we're looking for nu. So let's convert the 650 nanometers into meters first. 650 nanometers. I need nanometers to cancel, so I put nanometers on the bottom, meters on top. I put a 1 with the meter because it's larger, and there's 9 powers of 10 between the two. So that would give me 6.5 times 10 to the negative 7 meters. We can say that speed of light is equal to the wavelength times the frequency. And we're looking for the frequency, so the frequency is equal to the speed of light divided by the wavelength. So it's 3 times 10 to the 8th meters per second divided by 6.5 times 10 to the negative 7 meters. This will give us 4.62 times 10 to the 14. That will be hertz. In the next problem, find the wavelength of electromagnetic radiation with a frequency of 8.6 times 10 to the 11th hertz. So again, we're going to use this formula. Speed of light is equal to wavelength times the frequency. So the wavelength is equal to speed of light divided by the frequency. Okay, that will give us something like 3.49 times 10 to the negative fourth meters. And if you're asked to convert it to micrometers, I want meters to cancel. It goes on the bottom. Micrometers goes on top. 1 goes with the meters. There's 6 powers of 10 between those two. That would give me 349 micrometers. Okay, what is the energy of a photon or red light having a frequency of 4.48 times 10 to the 14th hertz? Looking for energy. So we know that energy is equal to Planck's constant times our frequency. It would be 6.626 times 10 to the negative 34th times 4.48 times 10 to the 14th. So my energy here is going to be 2.97 times 10 to the negative 19 joules. So what's the energy of an ultraviolet photon having a wavelength of 1.18 times 10 to the negative 8 meters? We're looking for energy. Okay, so we're going to take this formula that we just used. We're going to modify it a little bit, because we know that if C equals lambda times nu, then nu equals C over lambda. So let's substitute this here for nu. So E equals H times C over lambda. The energy is going to be 6.626 times 10 to the negative 34th times 3 times 10 to the 8th divided by 1.18 times 10 to the negative 8 meters. So this should give us 1.68 times 10 to the negative 17 joules. What is the wavelength for an electron having a mass of 9.11 times 10 to the negative 31st kilograms, traveling at a speed of 1.0 times 10 to the 7th meters per second? We have a mass of 9.11 times 10 to the negative 31st kilograms. We have a velocity 1.0 times 10 to the 7th meters per second. And we're looking for a wavelength. Using the formula, mass is equal to Planck's constant over the wavelength times velocity. We can get that the wavelength is equal to Planck's constant over the mass times velocity. Wavelength is equal to 6.626 times 10 to the negative 34th divided by the mass of the electron, which is 9.11 times 10 to the negative 31st kilograms, times the velocity of 1.0 times 10 to the 7th meters per second. So we get our wavelength is equal to 7.27 times 10 to the negative 11 meters. Thank you for watching. In the next video, we'll probably go into a lot more detail on the quantum mechanics used to map out electrons. Thank you for watching. Please like and subscribe, and I'll see you back soon.